Today we're going to cover chapter 24 on electric current, and we'll be able to cover this one in just one class, so it's not a very long chapter. Okay, we're going to cover everything in the chapter except conduction mechanisms, so I won't hold you responsible for that section. In this chapter, we're talking about current, and when we talk about current, the first thing we need is an electric circuit. And that simply means that we have a continuous conducting path, that our current can make it all the way from one side of the battery around to the other side. And so in this simple circuit where we've got a light bulb and a battery, obviously if we disconnect the wire, then we no longer have a continuous conducting path, so we no longer have an electric circuit, and we're not going to get a flow of charge. And that's what current is. So here's our definition of current. If the current is constant, we define the current as the amount of charge that passes through any point or passes through the wire at any point in a circuit. So for example, let's say that we've got this circuit here and we just look at the amount of charge going by this point. Well, if we figure out how much charge goes by there in a certain amount of time, delta t, that is the definition of the current. We can also define the instantaneous current if the current is not steady but is changing. And then, just as we've done so many times this year, we go from deltas to a derivative. And we'll need that definition of instantaneous current in the next chapter. So I want to look at this simple circuit where we've got our current going around like that. And the question is, where is the current greatest? Is it greatest at point A, point B, point C, or point D? Well, if you answered that it's the same everywhere, you were correct. So this is really important. In a series circuit, the current is the same everywhere. So don't forget that. We'll talk more about that actually in the next chapter. But in other words, once a charge leaves the battery and starts its way around the circuit, there's nowhere for it to go. So other than just around the circuit. And therefore, however much charge per second is leaving the battery has to be the amount of charge per second coming back to the battery. And therefore, the current has to be the same everywhere in the circuit. Now, there is something that changes as you go around the circuit, but that's the voltage. We'll come back to that next chapter. So we've already mentioned what our unit of current is in previous classes. The unit of current is the ampere, which usually we abbreviate as an amp. And 1 amp is equal to 1 coulomb per second. And we can see that just from our definition of current, that current is delta Q over delta T. All right, one of the things that is a little bit disturbing, I think when you first learn it, is how we define the direction of the current. Now, all through the course, we've talked about the fact that it's electrons that actually can move in metal. So if this is the negative side of the battery, then really what's happening in the circuit is that electrons are traveling from the negative terminal towards the positive terminal. However, in electronics and in all of physics, we define the current flow as the direction that positive charges would travel. So when I ask you what's the direction of the current in the circuit, think of it as the direction that positive charges would go. So in other words, a positive charge would go in that direction. And that's how we define current. So even though we now know that it's electrons going the opposite way, it's really completely equivalent to say positive charges go from plus to negative around the circuit. So again, if I ask you about the direction of current, it's always this conventional current definition. Let's do a quick problem just to get some practice with our formula here. It says a 60-watt light bulb will draw 0.5 amps of current when connected to 120 volts. If you leave the light on for 5 minutes, how much charge passed by any point in the circuit? Well, first of all, just to draw the circuit, we've got 120 volts. I'll represent that as a battery. And we've got our light bulb. So all we really need to know to solve this problem is we need to know the current and we need to know the time. If we want to know how much charge passes any point, we just can solve for delta Q. Delta Q is I times delta T. And you'll notice the only thing we have to be careful of here is just our units. So current is 0.5 amps, but we know an amp is a coulomb per second. And therefore, we've got to make sure that we take that 5 minutes and first convert it to seconds. So we know that there are 60 seconds per minute. And therefore, we can get the answer, which is 150 coulombs. And again, everywhere in the circuit, because it's a series circuit, the current is the same. So whether I count the amount of charge going by per second there, or right inside the filament of the light bulb, I would get 150 coulombs are passing in a 5-minute period. Let's take a look at what's actually going on inside the wire. So this is a microscopic view of the current. Now again here, we know it's really electrons that are traveling, but we're going to pretend that it's little positive charges that are traveling. Okay, so if you think about what the current depends on, it basically, if I just watch one point of the wire, it's how much charge per second goes by that one point in the wire. And so that's going to depend on how fast the electrons are moving. It's going to depend on how much charge each electron carries. It's going to depend on how many electrons there are in a given volume. It's also going to depend on how big the wire is, what we call the cross-sectional area of the wire. So let's see how these all fit together. We know that current is defined as the amount of charge per time. So ultimately what we're trying to do here is just figure out what is current in terms of what's going on inside the wire. To get us started with that, let's say that we look at a length of wire, L. Well, if our little charges are moving with a velocity, v subscript d, which we call the drift velocity, then it's true that the velocity is related to the distance those charges travel per time. So in other words, one of the charges that starts all the way over here travels a distance L in a certain amount of time. That would be equal to the velocity of that charge. And I'm going to flip this around and say the amount of time it takes for all of the charges in this section to get past this point in the wire is L divided by the drift velocity. So that's what delta T is equal to. Now, delta Q is the amount of charge that's going to go by this point. Well, in an amount of time delta T, all of the charge that's in here is going to pass that point. And so I just want to take the number of charges per volume, which we denote by little n, times the volume of that cylinder. Well, that's just the cross-sectional area times the length. And then that would be the number of charges, but I want the actual amount of charge. So I've got to multiply by Q, which is the charge on each of our charge carriers. So I'm now going to take that and divide it by the amount of time it takes for all those charges to go by that point. So that's L over the drift velocity. And you'll notice that the length of wire cancels out, which is good because we just randomly picked a certain amount of wire to look at. And what we get is the current is related to the number of charges per volume. That's going to be different for different metals. Okay, so that depends on the metal, times the cross-sectional area of the wire, times how much charge each of our charge carriers has. So that's just the charge on an electron, 1.6 times 10 to the negative 19th. And then times the drift velocity, how fast the electrons move in the metal. Okay, so we figured out that current is related to the density of the charges in the metal times the cross-sectional area of the wire, the charge on each of our charge carriers, and the drift velocity. So let's try out the following problem. You might want to go ahead and try it on your own. Pause the video and do that, and then come restart it and see what I got. Okay, so obviously what I want to do here is I want to take my formula and solve it for the drift velocity. So let me do that first. We've got the drift velocity is equal to I divided by NAQ. And so in this particular example, we've got a current of 10 amps. We're dividing by the number of charges per volume. So this is specifically for copper. Again, different metals would have a different value. 1.1 times 10 to the 29th. The cross-sectional area of my wire is 2 times 10 to the negative 6th. By the way, the reason I came up with that number is that's roughly like the wires we've been using in the lab. And then finally, I get 1.6 times 10 to the negative 19th for the charge on each of my charge carriers. Well, if you work that out, you should get 2.8 times 10 to the negative 4th meters per second. Now you notice that that's a very small velocity. That's 0.28 millimeters per second. Now, you might find that surprising that the electrons are traveling so slowly in the wires in a typical circuit. And in fact, it brings up an interesting question. If the electron drift velocity is so slow, why does the light turn on instantly when I flip the switch? So if you think about a circuit where I've got a switch and a light bulb and a battery, if those electrons are traveling so slowly around the circuit, why is it that the switch, when I flip that switch, the light turns on essentially instantly? Well, the reason for that is that the wire is full of electrons. And so in other words, when I close the switch, it's not like an electron right here has to get all the way around the circuit before the light goes on. All it has to do is bump the electron next to it and make it move. And that process is actually very fast. It turns out that the speed of current in a circuit is roughly a third of the speed of light. So it's actually very fast. That's the speed of the signal, but the electrons are going very slowly. Another analogy that I like to use when I think about this is I think about what happens with a garden hose. So if I connect my garden hose to an outdoor faucet, if it's the first time I've used that garden hose in a while, I turn on the faucet and it takes a long time before water starts coming out. On the other hand, if I've just used it recently, then the hose is still full of water. And so as soon as I turn the knob on, water starts coming out. Well, why is that? It's because the little water molecule that's right here, it doesn't have to get all the way down here. It just has to bump the one next to it, which bumps the one next to it, so one comes out. And water is essentially an incompressible fluid, which means that happens very quickly. Electrons in a wire are the exact same way. So as soon as this electron starts moving, it's an incredibly fast process for the one all the way over here to have to start moving. And that's why our lights turn on essentially instantly. Let's talk about Ohm's Law. Oftentimes, if you've learned Ohm's Law before, you probably remember it as V is equal to IR. And that's certainly a fine way to remember it. But I like students to think about it this way, much in the same way that when I first taught you F equals ma, I didn't write it that way. I wrote it as the acceleration is equal to the net force divided by the mass. And the reason I did that back last fall was to show you that it's force that causes acceleration, right? So independent variables here, dependent variable here. If I add a greater force, then my object is going to accelerate at a faster rate. Same thing with current, voltage, and resistance. A higher voltage causes a higher current. A current does not cause a voltage. Okay, so that's why I want you to always think about Ohm's law in this way. The other quantity here is resistance. And resistance is just what it sounds like. It's how easy or hard is it for current to flow through an object or a wire. Okay, and so just like the more mass an object has, the harder it is to get it to accelerate. The more resistance something has in a circuit, like a light bulb or a resistor, the harder it is to get current through that object. Resistance is measured in units of ohms, and we've got kind of a little inside physics joke here. The symbol that we use to represent resistance is the Greek symbol omega, and you'll notice you can think of it as ohm mega. Okay, so that's our little inside joke there, that we use the Greek letter omega to represent the symbol for resistance, which is ohms. You'll notice from this formula we see that an ohm is equal to a volt per amp. Now, I want to talk about an experiment we did in the lab. Depending on which section you're in, you may or may not have actually done this. So, for the Tuesday-Thursday section, the lab we did right before vacation, you measured the voltage and the current through 3 different objects: a light bulb, a resistor, and an LED. For those of you in the Monday-Wednesday section who have done the online version of the lab, I just had you plot this for a resistor. So let's start with that. When you plot V versus I for a resistor, you get a straight line. Notice that since V equals IR, if I plot V versus I, then the slope is equal to the resistance. And so when you plot V versus I for a resistor, you get a constant slope. And that's because a resistor is simply a device that has a constant resistance. Okay, so a resistor has a constant resistance. So when you go and buy a resistor, go and buy a resistor at an electronics store, you're buying a resistor, let's say, that has a value of 150 ohms. It's always going to have that value, and therefore, if you put various voltages across it, you're going to measure currents that are directly proportional. Now, when you do this for a light bulb, you actually get a different result. It's roughly linear, but what we found when we did it in the lab was that it went like this. You'll notice that since the slope is the resistance, what we find is that with a light bulb, the hotter the filament gets, the harder it is for electrons to pass through the filament. And that's why the slope increases here. It has a higher resistance with increasing temperature as we put more voltage across it and more current flows through it. An LED is a very interesting object. The circuit symbol for an LED looks like this. So it looks kind of like an arrow. And that's because an LED allows current to only flow in one direction. And it also requires a certain amount of voltage before it allows current to flow. So what we found for the LED was that up to a certain point, no voltage or no current flowed until we got to, it was around 2 volts for the LEDs that we used. And then all of a sudden we got a very flat curve. So with an LED, essentially it had an infinite resistance until it turned on at about 2 volts. And then notice its resistance went to 0. So with Ohm's law works for any component, but notice it's only a resistor where Ohm's law, or where the resistance is constant and you get a straight line when you plot V versus I. For other devices, you don't. Let's talk about electric power in a circuit. Remember from Physics 1 that the definition of power is it's the rate at which we use energy. So it's energy per time. And the unit for power is the watt. A watt is then simply a joule per second. What we want to figure out then is how much power is used in something like a resistor or a light bulb when we connect it in a circuit. And to do that, what we want to do is just remember that the amount of energy that is related to the charge and the potential difference. Again, when we saw this in chapter 22, we wrote it as delta U is equal to Q delta V. But again, remember, starting with the last chapter, what we used to mean by delta V, we now just denote as V, the electric potential difference. So since power is just the rate at which we use energy, I just want to take delta U and divide by delta T. Well, if we're looking at a certain amount of charge going through something like a resistor, that would be an amount of charge delta Q times the electric potential difference it goes through over delta T. But you'll notice that delta Q over delta T, that's current. And so what we get is that in a circuit, the power is simply equal to the current times the voltage. Let's do the following example. A 1600 watt hairdryer is plugged into a 120 volt outlet. How much current does it draw and what is the resistance? So we've got two different formulas. We have Ohm's law, that V equals IR. And we also have that power is equal to current times voltage. You'll notice that what we've been given is the power. So the power is 1600 watts. And we've also been given the voltage. To find the current then, we can just use this formula. Current is equal to power divided by voltage, or 1600 watts divided by 120 volts. And that gives us a current of 13.3 amps. By the way, that's a pretty significant current. Something like a hairdryer, toaster oven, anything that heats things uses a lot of current. Once we've got that, we can calculate the resistance. R is equal to V divided by I. And so we would take 120 volts, divide by the current of 13.3 amps, and we would get 9 ohms. All right, we're going to take a trip with our hairdryer. So we take our hairdryer and we take it on a trip to Europe. Now it turns out in Europe, the voltage is not 120 volts at the outlet, it's 240 volts. And that's true of many areas in the world outside of the United States. So it's just a different standard. But here's the thing. Our hair dryer was designed with a resistance of 9 ohms. And that is determined when that hair dryer is built. That's not going to change. So the question is, what happens if we now plug that in to a 240 volt outlet? Well, the current that it would draw would just be the voltage divided by the resistance. And that would be 240 volts divided by our resistance, which is still 9 ohms. That gives us a current of 26.7 amps. Notice that our hairdryer is now drawing twice the current that it was when we plugged it into 120 volts. If we look at how much power it's going to use, since power is current times voltage, notice that both the current and the voltage doubled. And that means the power is going to be 4 times what it was originally. So our hairdryer that was designed to use 1600 watts when plugged in the United States is now drawing a massive amount of energy per second. And what's going to happen is that hairdryer is either going to catch on fire or melt. And that's not a good thing. Usually when I teach this in class, I ask if anybody's had this experience. And oftentimes there'll be someone who has, who either because they're in the military or they've traveled a lot, they've taken devices to other countries and they've had this experience of destroying the thing that they're plugging in. So I want to talk just for a second about that. It turns out if you are traveling and you want to be able to plug in that hairdryer, you need something called a transformer. And a transformer will actually change the voltage from one level to another. And if you buy one of these kits, it comes with this big transformer that will take care of that for you. And of course, the other part of it is that the plugs that are used in different countries have different shapes. So you need the correct adapter. And usually all of these kits will come with all the adapters that you need. By the way, if you look at the charger for your cell phone or for your laptop, you might see written in small print on it that you can actually directly plug it in to anywhere between 100 and 240 volts. So in those devices, they already have this functionality built in so that you can use them worldwide. And most cell phones and laptop chargers have that capability. All you would need is the simple adapter to be able to plug it in a different country. Now, we haven't talked a lot yet about the difference between direct current and alternating current. Direct current simply means that the current only travels in one direction. So when I have a simple DC circuit, like a light bulb connected to a battery, as we know, the current leaves the positive side of the battery, so our current direction would be like that. And the current always has the same direction. Even if I vary the voltage on the battery, the current is always going to be traveling, in this case clockwise, around the circuit. So it can change, but it's always in only one direction. Alternating current means that the current actually starts in one direction in a circuit and then actually goes back the other way. So in an alternating current circuit, where we're plugging into something like the wall outlet and we connect a light bulb to the wall outlet, well, at one moment the current is going in this direction, and then a short time later it's going the opposite direction. And in fact, for household current in the United States, that frequency is 60 hertz. So if we were to graph the current as a function of time, we would see that it's much more complicated, that the current is going one direction and then back the other way. So the next question is, why is it that we don't use DC to power our homes? Why is it that we use AC voltage in our homes and businesses instead of DC? You'll notice that things like cell phones and laptops use DC because they just use batteries. Batteries are always DC. Well, usually when I ask this question in class, a lot of people have some ideas, but usually people don't know the details of why it is. So oftentimes people will tell me that AC travels long distances better than DC. And that's actually not true. But the answer is related to the concept of the fact that our power companies are far away from where we want to use the energy. And so it does have something to do with that, but it's not that DC can't travel as efficiently as AC can. So I'm going to leave that question for now, and we'll come back to it in a couple chapters once we have the rest of the physics we need to truly understand the answer. I want to talk a little bit about electrical safety. The first thing that I have on the slide here is a little bit disturbing. It doesn't take much current to kill someone. Notice that we're talking about very small currents. Death within minutes, 100 to 200 milliamps. Notice your hair dryer, as we just figured out, is using something like 13 amps. That's a tiny current, and that's enough to kill someone. So we want to look at how do we use electricity safely and why it is that we don't get electrocuted all the time. Well, here's the good news. Under dry conditions, the resistance of a person is very high. So the resistance of a person is like 10 to the 5th ohms. So think about this. If you do something really stupid like stick your finger in a wall outlet, well, the current that goes through you is still probably not going to kill you because current is V over I. And if we just do a really rough calculation, say the voltage there is about 100 volts, which is 10 to the 2, and we divide that by a resistance, got an R, I should have put an R there. We divide that by a resistance of 10 to the 5th. Notice that that gives us a current of 10 to the minus 3, or about 1 milliamp. So I don't know about you, but when I was a kid, I stuck like a paper clip into an outlet, and I got a bad shock, but it didn't kill me. You'll notice that it was in that threshold of sensation, and so I was okay. Now here's the problem. What if a young John had done the same thing, but I had just, come out of a pool and I was wet and my feet were really wet and I did the exact same thing? Well, now the problem is that the voltage is still about 100, but my resistance is also only about 100 ohms. And that means that I'm going to draw about 1 amp, and that's bad. Your professor would no longer be here. It's not very often I get to draw a skull and crossbones. This is really just to see if you guys are actually watching these videos. So there you go. Okay, so that's why we have to be really careful about electricity under moist conditions. And I'll show you how it is that the wiring in our homes helps protect us in those areas that can be more dangerous because of wet conditions. So what I want to do for the remainder of the chapter is just quickly talk you through how houses are wired. Now, big disclaimer, I'm not teaching you how to wire. There are lots of good books on that. You can often take classes on how to actually do some simple wiring. It's really kind of cool to be able to do it yourself. But here I'm really just trying to show you the physics behind how we can use electricity safely. So we'll answer all of these questions about what do circuit breakers do, why do our outlets have 3 prongs instead of 2, is it bad to use one of these cheater plugs if you only have wall outlets that have just the 2 prongs and not the ground prong. We'll also talk about what are those plugs that have the buttons on them, which are GFCI. So let's start at the beginning. When the electricity comes to your home, the first place that it goes to after it passes through the electric meter, which is usually outside, is it passes to the main breaker box, or what's sometimes referred to as the load center. Now, I'm sure most of you at some point in your lives have looked in the fuse box or the breaker box. That's what I'm talking about. What this first diagram shows you on the left is what is inside the breaker box. So that's what it looks like with all the breakers removed. It turns out that what actually comes into your house is 2 120 volt power lines. So 2 different hot lines and then a neutral line. And they connect to the back to what are called bus bars. So these bars are called bus bars. And so one side connects to this bus bar, one side connects to that bus bar, and then the neutral wire connects over here. Then when the electrician installs your setup, they then put in the circuit breakers and they connect to these metal tabs that you can see in here. Okay, so these metal tabs is where the circuit breakers connect. And then all of this is hidden from you so that you don't electrocute yourself when you go and flip a circuit breaker. So let's look at what it is that the circuit breakers do. The purpose of the circuit breaker is they're there to stop fires. So you think about the fact that you've got all this wiring in the walls of your house. We know that if you put too much current through a wire, it gets hot. So if we've got too much current flowing through a wire and that wire is inside the walls, that could easily start a fire. So a circuit breaker is designed so that it opens up if the current gets beyond a certain value. And as we'll see in just a second, most of the circuits in your home are going to be either 20 amp circuits or 15 amp circuits. So if you draw more than that amount of current, the circuit breaker opens up. It's kind of cool the way they actually work. What's inside the circuit breaker is something called a bimetallic strip. And a bimetallic strip is just what it sounds like. It's 2 different types of metal that are bonded together. Now, what happens when you heat up a bimetallic strip, and it will heat up if too much current goes through it, because the different metals have different expansion rates, the metal that expands more will push the other metal over. In other words, it will make that strip bend. And what that does is it opens up this contact point. So normally the electricity flows through the bimetallic strip and flows out to your circuit. But if too much current flows through, the bimetallic strip bends and it opens that contact point. The nice thing about circuit breakers is once you fix the problem, you just can flip them and it resets them. Older homes use fuses, and fuses work well too. It's just that the way they work is there's a piece of metal that simply burns up if you put too much current through it. The problem there is you got to go buy a new fuse when that happens. Okay, so how are things actually wired? So again, as I mentioned previously, coming in from the power company are actually three wires, two different 120 volt wires, and then what's called the neutral wire. Now, the reason we have two 120 volt circuits coming into our homes is that certain appliances require 240 volts, like an electric stove or an electric clothes dryer. And so the way that works is the electric stove connects to the two different 120 volt lines. They're out of phase, so that when you connect across the two of them, you actually get 240 volts. However, a regular outlet, that's a 120 volt outlet, connects to just one of the 220 volt lines, and that always connects to this blade. That's the hot blade. Then this blade is connected to the neutral wire. The neutral wire is grounded when it comes into your home, and if you live in an apartment building, you might not be able to see this. If you live in a home, you can usually see a grounding stake near the electric meter where that connection is actually made. Okay, so you may or may not be able to see that where you live. All right, you'll notice that when we wire a three-prong outlet, both what's called the ground and the neutral actually connect to the same place in the breaker box. That neutral wire that's coming in from the power company and is physically connected to a stake going into the ground right at your house. A little bit later on, we'll talk about why it is that having this third connector, even though it's going to the same point in the box, gives you some added protection. If we look at household circuits, on any given circuit, there's usually more than one plug. So we've got our fuse or circuit breaker, and then this is going back to the neutral wire. And then each outlet or a light bulb with a switch is connected in parallel with those two wires. And obviously you can see why we want to connect them in parallel. We always want the voltage to be the same. So I always want to know that when I plug in, I get 120 volts. Notice, by the way, if we instead wired things in series, if I wanted to use my hairdryer, I'd have to turn on my stereo receiver and my electric heater to make it all work, which obviously wouldn't make sense. So outlets on a given circuit are connected in parallel. Now, by the way, you'll notice here I've got an electric heater and a hairdryer. If I turn both of those on at the same time, I'm going to draw too much current and it's going to blow the fuse or pop the circuit breaker. So as I mentioned previously, most circuits are going to either be 20 amp circuits or 15 amp circuits. And what determines which type of breaker or fuse you have is simply dependent on the underlying wire. A fatter wire can carry more current. So a 12 gauge wire is a thicker wire. It's more expensive to install, but it can safely carry a higher current than a 14 gauge wire can. Okay, just a couple more slides. I want to talk about the purpose of that extra ground wire. So here you are. It turns out that you really like your microwave oven. And every morning you come out and you give it a nice love pat. And of course, you're here in your bare feet, but that's not a problem. You know, your microwave works nicely. You give it a pat each day. But then one day you come out and from tapping it every day for many days, all of a sudden, one of the wires comes loose in that microwave. And it turns out, unfortunately, it's the hot wire, and that wire makes contact with the inside of the metal case. Well, you'll notice that now the electricity is going to flow through the metal case, through you, and back to ground this way. Because remember, the neutral wire is literally connected to the ground. If you're standing on the ground, you are essentially always connected to the neutral wire. And so if you touch the hot wire, that 120 volts is now going across you, and depending on, if your feet are wet and your hand is wet, that might be enough to kill you. Well, obviously, we don't want people dying when they pat their microwaves. So here's the way we prevent that. What the third prong in the outlet is for is it is a separate connection back to ground, back to the neutral wire. And inside your appliance, if you take apart an appliance, you'll find that that third prong, that wire is always connected directly to the metal case. And so here's what happens. Even if a wire breaks inside the microwave and touches the inside of the metal case, the current will flow through the case through that third wire back to ground. That has very little resistance compared to your resistance. And so none of the current will flow through you. Now you'll notice that some appliances only have two-prong plugs, and some appliances have three-prong plugs. That has to do with whether they have metal cases or not. Non-metal appliances in general, if there's no metal that you can touch that is susceptible to being connected to a short, then a two-prong plug is fine. But if the appliance has metal and there's any way the electricity inside can contact that metal, that's when you need a three-prong plug. Now, those cheater plugs that take a three-prong plug and switch it into a two-prong, and again, just to make sure you know what I'm talking about one of these. So if you have an older house, sometimes you'll have outlets that are only two prongs. Generally, these are not a good idea because effectively you're taking away the safety feature. And you really probably want to get an electrician to look at that and see if you can upgrade those two-prong outlets to three-prong. Okay, the last thing I want to talk about is the concept of a GFCI. Remember that we know we're most likely to get hurt by electricity if we're in a damp environment. And so certainly kitchens, bathrooms, garages, basements are all places where there's likely to be moisture in the environment. So that's where we have to be extra careful. And so what a GFCI does, and again, these are those outlets that have the little buttons on them, is they look to see if any of the electricity is going somewhere it shouldn't go. And here's what they do. They basically monitor the current coming out and coming back through the wires that it's supposed to go through. And let's say that we've got our person here and we've got some problem with this appliance so that we get a ground fault, meaning that there's not that safety ground to take the electricity safely back, and it starts flowing through our person. Well, what our GFCI device does is it monitors the current going out and coming back from the appliance. And if there's even the tiniest mismatch, then what it does is it opens up the circuit. And so that little thing will pop and all of a sudden no electricity will flow. And that way our person is stopped from getting electrocuted. So we have those extra protections anywhere where we've got moisture. One of the things about garages or basements that's often dangerous is just concrete. If you're standing on a concrete floor, you'll often notice they feel very damp. They attract moisture. And so being barefoot on a concrete floor is really something you don't want to do when you're working with electricity. And so again, that's why in any new construction, you have to have GFCI devices in any of those locations. You can also install them after the fact as if you upgrade the wiring in a house. All right. That's all I want to say. That's the end of chapter 24.